The most precise measurement in the history of science still cannot reach it. Physicists have measured the charge of an electron to 12 decimal places. They have timed the oscillation of cesium atoms accurately enough to lose 1 second every 300 million years. They have tracked the positions of spacecraft drifting past Neptune to within a few kilometers. Precision, in modern physics, has become almost unreasonable. And yet there is a length so small that no measurement has ever approached it, not because the instruments are crude, but because the act of measuring changes what you are trying to measure. Below a certain scale, the energy required to look at something becomes large enough to bend the space around it. You stop probing the territory. You start rewriting it. That scale sits roughly 20 orders of magnitude below the diameter of a proton. 20 orders of magnitude, meaning if a proton were the size of the observable universe, the Planck length would still be smaller than a grain of sand inside it. Tonight we move toward that scale carefully, one layer at a time. The universe has a rule about visibility, and it is not negotiable. A wave can only resolve a detail that is roughly the same size as its own wavelength, or smaller. If the wavelength is longer than the object you are trying to see, the wave simply moves past it. The object leaves no impression, creates no disturbance, might as well not exist as far as the wave is concerned. Think of it this way. Out on open water, a long ocean swell, the kind that stretches 100 meters from crest to crest, rolls across a small rock just below the surface without registering it at all. The swell lifts, travels, falls, and the rock was never there as far as the wave was concerned. But send a series of short ripples across that same surface, ripples with a wavelength of a few centimeters, and the rock becomes visible in the wave pattern. The ripples scatter, reflect, leave a signature in the water around it that someone watching from above could read. The rock did not change. The wave changed, and that change in the wave is what made the rock real to an observer. This is not a metaphor for how microscopes work. It is the actual mechanism. Visible light, the light your eyes are built to detect, has wavelengths ranging from about 400 to 700 nanometers. A nanometer is 1/billionth of a meter. To give that scale some weight, a human hair is roughly 80,000 nanometers wide. A red blood cell is about 8,000 nanometers across. An atom of hydrogen, the smallest atom in existence, is about 1/10 of a nanometer wide, which means visible light has a wavelength roughly 4,000 times longer than the atom you are trying to see. The atom is the submerged rock. The light wave rolls over it without registering anything. This is why no optical microscope, no matter how carefully engineered, no matter how precisely its lenses are ground, has ever directly imaged an individual atom. The constraint has nothing to do with the quality of the glass or the steadiness of the stage. It is built into the wavelength of the light itself. So the question becomes, what do you use instead? In the early 20th century, a French physicist named Louis de Broglie proposed something that, at the time, had no experimental support at all, only the internal logic of the equations. He argued that if light, which everyone had assumed was purely a wave, could also behave as a particle, then perhaps the reverse was also true. Perhaps particles, things with mass, things that occupy space, things that bounce off other things, could also behave as waves. And if they did, their wavelength would depend on their momentum. Faster-moving particles would have shorter wavelengths, and shorter wavelengths would resolve finer detail. The idea was published in 1924. 3 years later, it was confirmed by accident. Clinton Davison and Lester Germer, working at Bell Laboratories in New Jersey, were studying how electrons scatter off a nickel surface when a piece of laboratory equipment failed and exposed their nickel sample to air. The surface oxidized. To restore it, they heated the sample to high temperature, and in doing so, accidentally transformed the nickel from a mass of small disordered crystals into a few large ordered ones, with atoms arranged in clean, repeating rows. When they resumed their electron scattering experiment, the data looked completely different from anything they had seen before. The electrons were no longer scattering randomly. They were producing a pattern, peaks of intensity at specific angles, troughs of near-zero intensity between them. It was a diffraction pattern, the same kind of pattern that light produces when it passes through a grating with slits spaced at intervals comparable to the wavelength of the light. The electrons were diffracting off the rows of atoms in the crystal, the way light diffracts off a diffraction grating. Matter had a wavelength. What this meant, practically, was that a beam of electrons accelerated to the right energy would have a wavelength short enough to resolve individual atoms and would do so using far less energy than a photon of equivalent wavelength would require. An X-ray photon short enough to match atomic scales carries around 12,000 electron volts of energy, enough to ionize atoms, to knock electrons free, to chemically alter the very sample you are trying to study. An electron achieving the same resolution needs only a few hundred electron volts. The electron is, in this sense, a much quieter instrument, capable of resolving the same detail while disturbing the subject far less. The first electron microscopes followed in the 1930s, and within a few decades they were revealing structures no human eye had ever seen: the surface topology of viruses, the lattice geometry of crystals, the internal membranes of living cells. Each image was made not from reflected light, but from scattered electrons, their wave behavior recorded and translated into something visible. But the deeper consequence of de Broglie's idea was this: if particles have wavelengths, and if wavelengths can be shortened by increasing energy, then the rule that governs visibility is the same whether you are using light or matter. Higher energy, shorter wavelength, finer resolution. The two domains, light as a probe, matter as a probe, obey the same underlying logic. This meant that to look inside the nucleus of an atom to see what protons and neutrons were made of, if they were made of anything at all, you needed not just an electron microscope, but something far more powerful. You needed electrons accelerated to energies billions of times higher than the electrons that resolved atomic structure. You needed something that had never been built before. In the 1960s, a 2-mile-long accelerator in California began firing electrons at protons with energies in the range of tens of billions of electron volts, energies that gave those electrons wavelengths far shorter than the diameter of the proton itself. What the experimenters expected to see, if the proton were a uniform solid sphere, was smooth, predictable scattering, electrons bouncing off the surface with angles and energies that followed a simple distribution. What they saw instead was something else entirely. The electrons were scattering at large angles, bouncing back sharply, as though they had struck not a smooth sphere but small, hard, concentrated points of charge inside the proton. The scattering pattern was irregular, point-like, nothing like the behavior of a uniform solid. The proton had an interior, and the interior had structure. The hard points the electrons were bouncing off would eventually be identified as quarks, particles that Murray-Gell-Mann had proposed on theoretical grounds a few years earlier, but that no experiment had yet confirmed as real. Now they were real. The proton was not a fundamental particle, but a composite one, built from 3 quarks bound together by a force so strong and so strange that it behaved unlike any force known before it. The rule had held again. More energy, shorter wavelength, another layer of structure uncovered. From cells to atoms to nuclei to quarks, the same principle had carried physics deeper each time it was applied. The question that nobody had yet been forced to answer clearly was whether the rule had a limit. Not a technological limit, not merely a question of whether we could build a machine powerful enough, but a limit written into the physics itself. Whether there was a scale, somewhere below the quark, where pouring in more energy would stop revealing new structure and start doing something else entirely. The same rule that governs what your eye can see, that a wave cannot resolve a detail smaller than its own wavelength, also governs what every microscope ever built can see. The eye evolved to detect light with wavelengths between roughly 400 and 700 nanometers, and that range happens to be useful for navigating a world of objects the size of leaves and faces and predators. It is not useful for atoms. An atom of hydrogen is about 1/10 of a nanometer across, roughly 4,000 times smaller than the shortest wavelength of visible light. Shining visible light on an atom and expecting to see it is like trying to feel a single grain of sand by pressing on it with the flat of your palm. The grain is simply not large enough to register. X-rays were the first serious attempt to breach this limit. In 1912, a physicist named Max von Laue directed X-ray beams at a crystal of copper sulfate and observed something that had never been seen before: a diffraction pattern, a precise arrangement of spots and rings produced by the X-rays, scattering off the regular rows of atoms in the crystal lattice. The pattern was not random. Its geometry encoded the spacing between atoms, the angles of the lattice, the three-dimensional arrangement of the crystal's interior. X-rays had wavelengths short enough to interact with atomic scale structure, and they left a record of that interaction in the scattered light. For the first time, human beings had indirect evidence of how atoms were arranged in space. But X-ray crystallography revealed structure without imaging it directly, and it came with a cost. A photon carrying a wavelength short enough to resolve atomic detail carries roughly 12,000 electron volts of energy. To give that number some grounding, the energy needed to remove a single electron from a hydrogen atom is about 13.5 electron volts. A photon with 12,000 electron volts carries nearly 1,000 times that energy, enough to strip electrons from atoms, break chemical bonds, and alter the very crystal structure the experiment was designed to study. The probe was not gentle. It left marks. This is the tension that runs through all high-resolution imaging at small scales. To see a detail, you must interact with it. To interact with it at atomic scales, you must use a probe whose wavelength matches those scales. And a probe with a short enough wavelength carries enough energy to disturb what it touches. The act of observation is never perfectly passive. At atomic scales, it becomes actively intrusive. What changed this calculus was de Broglie's proposal, published in 1924, that particles with mass also have wavelengths. Not metaphorically, physically. A moving electron has a wavelength determined by its momentum. The faster it moves, the shorter its wavelength becomes. The relationship is the same one that governs photons. The difference is that an electron, being a massive particle, reaches a given wavelength at a much lower energy than a photon of the same wavelength would require. An electron with a wavelength short enough to resolve atomic structure needs only a few hundred electron volts, roughly 60 times less energy than an X-ray photon, achieving the same resolution. The electron reaches where the photon reaches, but arrives more quietly. The experimental proof came 3 years later, in 1927, through what was partly an accident. Clinton Davison and Lester Germer, working at Bell Laboratories in New Jersey, had been firing electrons at a nickel surface for months when their vacuum chamber cracked, exposing the nickel to air. The surface oxidized. To restore it, they heated the sample and, in doing so, inadvertently converted the nickel from a disordered mass of tiny crystallites into a few large single crystals with atoms sitting in clean, regular rows. When they resumed the experiment, the scattering pattern had transformed entirely. Instead of the broad, diffuse distribution they had seen before, The electrons were scattering in sharp peaks at specific angles, with regions of near-zero intensity between them. It was a diffraction pattern, the kind produced when a wave passes through a grating whose spacing is comparable to the wave's wavelength. The atoms in the crystal were acting as the grating, and the electrons were acting as the wave. De Broglie's wavelength formula predicted exactly which angles the peaks should appear at, given the energy of the electrons and the known spacing of atoms in the nickel lattice. The prediction matched the data. Matter had a wavelength, and it was measurable. Ernst Ruska, working in Berlin, recognized what this meant for imaging. If electrons have wavelengths, and if those wavelengths can be shortened by accelerating the electrons to higher energies, then in principle you could build a microscope that used electrons instead of light, one that could resolve details far smaller than any optical instrument. By 1931, he had built a working prototype using magnetic fields as lenses to bend and focus the electron beam. The images it produced were blurry by modern standards, but they resolved detail that no optical microscope had ever reached. Within a few years, electron microscopes were revealing the surface structure of materials, the geometry of crystals, the internal architecture of biological cells. What strikes me about this particular history is that none of it was inevitable. Davison and Germer found their result because their equipment broke. De Broglie published his wavelength hypothesis without a single experimental confirmation to support it. Ruska built his first electron microscope as a graduate student without institutional support, on the hypothesis that a 4-year-old theoretical idea was correct. The experimental confirmation of matter waves and the technology it enabled came from people following an idea into territory where the evidence had not yet arrived. The principle that emerged from all of it was clean and durable. Whether you use photons or electrons or any other particle as a probe, the rule is the same. Shorter wavelength resolves finer detail, and shorter wavelength requires more energy. The two are linked, and neither can be changed without changing the other. This is not a contingent fact about the probes we happen to have available. It follows from the wave nature of matter itself, from the same quantum mechanics that governs the behavior of every particle in the universe. By the 1960s, this principle had been pushed further than Ruska or Davison or de Broglie could have anticipated. Accelerators were producing electron beams with energies not in the hundreds of electron volts needed to resolve atoms, but in the billions, enough to drive wavelengths short enough to probe the interior of the proton itself. What those experiments found hard, point-like scattering centers inside what had been assumed to be a simple sphere, opened the question that the energy wavelength rule had always been building toward. If the proton has an interior, what governs how deep you can go? The rule says more energy reaches smaller scales. The question is whether there is a scale at which more energy stops working, where the rule that has held from the wavelength of light down to the interior of the proton finally meets something it cannot pass through. The proton had been assumed to be fundamental for decades. Not because there was strong evidence for this, but because no one had yet built an instrument capable of testing the assumption at the energies required to settle it. The proton was small, dense, and electrically charged, and it held the nucleus together against the repulsion of other protons. That was what was known. What was inside it, if anything, was a question that the physics of the 1940s and 1950s could not yet reach. Ernest Rutherford had established in 1911 that the atom itself was mostly empty space. His experiment involved firing alpha particles, helium nuclei, at a thin sheet of gold foil and observing where they went. Most passed straight through, which confirmed that most of the atom was open volume. But a small fraction bounced back at large angles, some nearly reversing direction entirely. The only explanation consistent with this pattern was that almost all the atom's mass was concentrated in a region vastly smaller than the atom itself, a dense core that the alpha particles were occasionally striking, head-on, That core was the nucleus, and it occupied roughly 100,000th of the atom's diameter. If an atom were the size of a football stadium, the nucleus would be a marble at the center. Rutherford's method: fire a probe at a target. Read the structure of the target from the way the probe scatters became the template for every deep structure experiment that followed. The logic is the same whether the probe is an alpha particle or an electron or a beam of X-rays. You learn the shape of what you cannot see by measuring how something else bounces off it. A blind person mapping a room by sound uses the same principle. The echo carries the geometry. By the early 1960s, theorists had begun to suspect that the proton and neutron might not be the bottom of the hierarchy. The reason was an embarrassment of particles. Accelerators built in the preceding decade had produced dozens of new short-lived particles: pions, kaons, lambda particles, sigma particles, and the list kept growing. It was difficult to believe that nature required so many truly fundamental particles. In 1964, Murray Gell-Mann and, independently, George Zweig proposed a solution. All of these particles could be explained as combinations of a small number of more fundamental constituents. Gell-Mann called them quarks, borrowing the word from a line in James Joyce's Finnegan's Wake. 3 quarks, combined in different ways, could account for the proton, the neutron, and the entire zoo of short-lived particles that accelerators had been producing. The proposal was mathematically elegant. It was also, at the time, entirely unconfirmed. Quarks were a bookkeeping device, a way of organizing the particle zoo into a coherent pattern. Whether they were real objects that physically existed inside protons, or merely a convenient mathematical fiction, was a question the theory alone could not answer. That required an experiment. The experiment was run in 1968 at a 2-mile-long accelerator in California. Electrons were accelerated to energies in the range of tens of billions of electron volts, energies that gave them de Broglie wavelengths far shorter than the diameter of the proton, and fired at a target of liquid hydrogen, liquid deuterium. Each hydrogen nucleus is a single proton. Each deuterium nucleus contains 1 proton and 1 neutron. The electrons would scatter off whatever was inside. If the proton were a uniform sphere of charge, the scattering would be smooth and predictable. The electrons would deflect at angles consistent with a diffuse, spread-out distribution of matter, and the probability of large-angle deflections, electrons bouncing sharply backward, would fall off rapidly with angle. This is what happens when a wave scatters off something soft and extended. The wave bends gradually around the obstacle. It doesn't bounce. What the detectors recorded was the opposite. Large-angle scattering was far more frequent than a uniform sphere could produce. Electrons were bouncing back sharply, at rates that implied they were striking small, hard, concentrated objects inside the proton rather than a smooth, continuous distribution. The pattern was unmistakable to anyone who had seen Rutherford's gold foil results 40 years earlier. It was the same signature large-angle backscattering that Rutherford had used to identify the nucleus inside the atom. Now the same signature was appearing inside the proton itself. The proton had constituent. 3 of them, it turned out, matching the structure Gell-Mann and Zweig had proposed. Quarks were not a mathematical convenience. They were physically real objects that electrons could bounce off. Objects with their own charge and their own momentum, confined inside the proton in a way that prevented any of them from escaping. That last point confinement turned out to be one of the strangest features of the strong force. Most forces in nature weaken with distance. Gravity between 2 objects drops off as the square of the distance between them. The electromagnetic force follows the same rule. The strong force does neither. At very short distances, when quarks are close together inside the proton, the force is actually weak, and quarks move almost freely. But as you attempt to pull 2 quarks apart, the force between them increases rather than decreasing. It behaves less like gravity and more like a rubber band under tension. The further you stretch it, the harder it pulls back. Stretch the rubber band far enough and it snaps. But when the strong force snaps, something different happens. The energy stored in the stretched force field is enough to spontaneously create a new quark-antiquark pair from the vacuum. The original quark does not escape. Instead, the new quark attaches to it, forming a new composite particle. The result is always two bound objects, never a free quark. No matter how much energy you invest in trying to liberate a single quark, the force converts that energy into new quarks, rather than releasing the original. Every quark that has ever been produced in an accelerator has been immediately captured into a new composite particle before it could travel any measurable distance. This is why, more than 50 years after the 1968 experiment established their existence, no one has ever detected a free quark. They are real. They have been probed extensively. Their properties are known with precision, but they have never been seen in isolation. They exist only inside other particles, permanently bound by a force that grows stronger the harder you pull against it. The interior of the proton, as subsequent experiments have mapped it, is not the tidy arrangement of three static quarks that early models suggested. The three quarks called valence quarks are embedded in a dense sea of transient quark-antiquark pairs that continuously appear and annihilate, and of gluons, the particles that carry the strong force between quarks. At any given instant, the proton contains not three particles but a fluctuating population of dozens, appearing and vanishing on timescales so short that the proton's diameter, at the speed of light, takes longer to cross than the lifetime of most of those virtual particles. The proton is less a fixed object than a sustained process, a standing pattern of quantum activity that looks stable from the outside but is in a state of constant internal motion. The energy scale at which quarks were first resolved around 1 billion electron volts corresponds to a probe wavelength of roughly 1 femtometer, about the diameter of the proton itself. 1 femtometer is 10 to the minus 15 meters. A proton fits inside an atom the way a marble fits inside a football stadium. The experiment in 1968 was probing, for the first time, distances smaller than the proton's own diameter. Each layer of structure had required a proportional increase in probe energy. Atomic structure became visible at hundreds of electron volts. Nuclear structure required millions. Quark structure required billions. The pattern was consistent, and it raised a question that no one at the time could answer from experiment alone. Whether quarks themselves had constituents, and if so, what energies would be needed to see them, and whether there was some scale at which the energy resolution rule would stop working entirely. The tunnel runs 27 kilometers in a circle, buried about 100 meters beneath the border between France and Switzerland. It took a decade to build, involved contributions from more than 100 countries, and houses the coldest large-scale system in the known universe, superconducting magnets cooled to 1.9 Kelvin, a temperature colder than the void between galaxies. All of this engineering exists for a single purpose: to accelerate protons to energies so high that their de Broglie wavelengths shrink to scales smaller than any structure ever directly probed before. Each proton in the Large Hadron Collider reaches an energy of around 7 trillion electron volts. 7 trillion electron volts is a number that resists intuition, so consider it this way. A single proton at rest has a rest mass energy of about 938 million electron volts, roughly 1 billion electron volts. The collider accelerates each proton to an energy 7,000 times larger than its own rest mass. That is the equivalent, in rough terms, of taking an object and giving it a kinetic energy 7,000 times greater than the energy locked in its own matter. Two beams of these protons, traveling in opposite directions, collide head-on, producing a combined energy at the collision point of 14 trillion electron volts. At that energy, the de Broglie wavelength of the colliding particles shrinks to about 1/100th of a femtometer, 1/100th of the proton's own diameter. The collider is not just reaching inside the proton. It is probing the behavior of the fields that hold the proton together at scales where those fields themselves begin to show structure. What the collider found at those energies, confirmed in 2012 after decades of theoretical prediction, was the Higgs boson. Understanding what the Higgs boson is requires stepping back from particles for a moment and thinking about fields. Space is not empty. It is filled with fields: the electromagnetic field, the strong field, the weak field, and others that permeate every point in the universe simultaneously. Particles are not objects moving through these fields. They are excitations of the fields themselves, localized disturbances that travel and interact according to the rules each field obeys. The Higgs field is one of these. It has a non-zero value everywhere in space, unlike most fields, which are zero in the absence of a particle. This constant background value is what gives certain particles their mass. An electron, moving through space, is constantly interacting with the Higgs field, and the strength of that interaction determines how much resistance the electron has to acceleration, which is what we measure as mass. Particles that interact strongly with the Higgs field are heavy. Particles that don't interact with it at all, like photons, have no mass. The Higgs boson is a ripple in this field. Like any field, the Higgs field can be disturbed, and a sufficiently energetic disturbance produces a quantized excitation, a particle. But the energy required to create that excitation is enormous, around 125 billion electron volts. To put that in context, it is roughly 130 times the rest mass energy of a proton. No accelerator before the Large Hadron Collider had reached energies high enough to disturb the Higgs field strongly enough to produce its boson. The field had been there all along, giving mass to every particle in every atom of every object that has ever existed, but the ripple it could produce had never been seen. Producing the Higgs boson at the collider is not a straightforward process. The boson is unstable, decaying almost immediately into other particles within a timescale so short that light, traveling at the speed of light, could cross the width of a proton roughly 10,000 times in the same duration. It cannot be detected directly. What the detectors record are the decay products, pairs of photons, pairs of leptons, jets of quarks, and from these fragments, physicists reconstruct what must have briefly existed at the moment of the collision. It is like reading a word from the letters scattered after it was written, then erased, then written again, then erased again, 1 billion times per second. The detectors that do this reconstruction are among the most complex instruments ever built. The two largest one, a cylinder 7 stories tall and 46 meters long, the other roughly the same dimensions but built with different technology to provide independent confirmation, each contain tens of millions of sensors. Every proton-proton collision produces hundreds of secondary particles, and there are roughly 1 billion collisions per second. Most collisions produce nothing of interest. A small fraction produce something worth recording. A smaller fraction still produce a Higgs boson. Identifying those rare events in real time, discarding the rest, and storing the survivors for analysis required building a filtering system that processes more data per second than almost any other system on Earth. The confirmation of the Higgs boson completed something. The theoretical framework, describing all known particles and the forces between them, built over 5 decades of experiment and calculation, had predicted the Higgs field as a necessary component. Without it, the mathematics produced particles with no mass, which contradicted everything observed. With it, the framework held together. Finding the boson meant the field was real, the framework was consistent, and the description of matter at the scale of quarks and fields was, in at least one important sense, complete. That completeness is worth pausing on because it is unusual in physics. Most theoretical predictions are confirmed piecemeal, with experiments nudging the picture forward incrementally. The Higgs was different. It had been predicted in 1964, and the prediction was precise enough that when the boson was finally found, its measured properties matched the theoretical expectation closely. Nearly half a century between prediction and confirmation, with the theory unchanged throughout. And yet the framework that the Higgs completed is also, in a different sense, known to be incomplete. It describes 3 of the 4 fundamental forces: electromagnetic, strong nuclear, and weak nuclear, but not gravity. It accounts for the matter we can see and interact with, but provides no explanation for the matter whose gravitational effects are visible throughout the universe, yet whose nature remains entirely unknown. It describes the behavior of particles at the energies accessible to current accelerators, but makes no prediction about what happens at energies many orders of magnitude higher. The collider has continued searching. Theories extending beyond the known framework predict additional particles, heavier versions of known particles, new force carriers, particles that could account for the unidentified matter that makes up most of the universe's mass. None have been found. The searches have ruled out large regions of theoretical possibility, which is itself information, but the data have not yet pointed clearly toward what comes next. What the collider represents, in the context of the energy resolution rule that has driven physics from the optical microscope to the present, is both a culmination and a reminder. It is the most powerful implementation of that rule ever built, the highest energy, the shortest wavelength, the finest resolution yet achieved. And it sits at energies 15 orders of magnitude below the scale where the rule itself is expected to break down. 15 orders of magnitude is the difference between the diameter of a proton and the diameter of the observable universe. Between what the collider can reach and the scale where the energy resolution rule fails, there is a gap larger than any gap between scales that physics has ever bridged. General relativity makes a claim that sounds unremarkable until you follow it to its conclusion. Energy curves spacetime. Not just mass energy in any form, including the kinetic energy of a moving particle, including the energy concentrated in a beam of light, including the energy packed into a small region of space by a high-power probe. All of it contributes to space-time curvature, in proportion to its magnitude. At the energies of everyday life, and even at the energies of particle accelerators, this curvature is so small it produces no measurable effect on the experiment. The geometry of the region being probed remains, for all practical purposes, flat. But the energy required to probe progressively smaller scales grows without bound, and the region being probed shrinks at the same time. This combination, more energy, smaller volume, means the energy density inside the probed region increases far faster than the energy alone. At some point, the curvature that energy produces is no longer negligible. At some further point, it becomes the dominant feature of the experiment. The specific threshold where this happens can be calculated. In general relativity, any mass or energy distribution has what is called a Schwarzschild radius, the size to which it would need to be compressed for the resulting gravitational field to prevent light from escaping. For the Earth, that radius is about 9 millimeters, roughly the size of a marble. The Earth is not compressed to the size of a marble, so it does not form a black hole. But if it were, the gravitational field at the surface would be strong enough that nothing, no light, no signal, no information could leave. The interior would become causally disconnected from everything outside. Now apply this to a measurement. To probe a region of space of size d, you need a probe with wavelength comparable to d, which requires energy roughly equal to the energy of a photon of that wavelength. As d shrinks, the required energy grows. At the same time, you are concentrating that energy into a region of size d, The Schwarzschild radius of that energy is proportional to the energy itself. So as d shrinks, the energy grows, and the Schwarzschild radius of the energy grows with it. There is a point where these two quantities, the size of the region being probed and the Schwarzschild radius of the energy doing the probing, become equal. At that point, the energy required to resolve the region is exactly the energy that would cause the region to collapse into a black hole. The probe and the region it was meant to observe disappear behind an event horizon. The measurement fails not because the detector was imprecise, not because the beam was misaligned, but because the act of probing created a gravitational boundary that hid the result. Adding more energy past this point does not help. It makes the black hole larger. The region that was already hidden behind a horizon becomes hidden behind a larger one. Resolution does not improve, it regresses. The instrument has crossed from a regime where more energy reveals more structure into a regime where more energy produces less information. The scale at which this crossover occurs is the Planck length. Its value, approximately 1.6 times 10 to the minus 35 meters, is not arbitrary. It emerges from combining three fundamental constants: the speed of light, which sets the relationship between energy and wavelength; the gravitational constant, which sets how strongly energy curves spacetime; and Planck's constant, which sets the minimum energy of a probe at a given wavelength. These three constants, combined in the only way that produces a unit of length, give the Planck length. It is the scale at which all three, electromagnetism, gravity, and quantum mechanics, become simultaneously important, and at which the assumptions underlying our current theories simultaneously break down. To appreciate the distance between where our best instruments currently reach and where the Planck length sits, consider the following. The Large Hadron Collider probes distances of about 1/100th of a femtometer, roughly 1/100th of the proton's diameter. The Planck length is 20 orders of magnitude smaller than that. 20 orders of magnitude is the ratio between the diameter of the observable universe and the diameter of a single proton. The gap between what the collider reaches and what the Planck scale represents is, in logarithmic terms, as large as the entire known hierarchy of scales, from the largest structure in the universe down to the smallest particle we have ever resolved. To reach Planck energies with a circular accelerator designed on the same principles as the Large Hadron Collider, scaled up proportionally, the ring would need to be several thousand light-years in circumference. A light-year is roughly 9.5 trillion kilometers. The accelerator would need to be larger than the distance from the Sun to the nearest star cluster, larger than most of the structures visible to the naked eye in the night sky. And even if such a machine could be built, the physics argument suggests it would not work, that at Planck energies, the collision would produce a black hole rather than a measurement. There is something worth sitting with in this. Every previous limit on our ability to see smaller things was a technological limit. We needed better lenses, stronger magnets, higher voltages, more precise detectors. Each of those limits was in principle surmountable, and most of them were eventually surmounted. The Planck scale is different. The argument that stops us there is not about technology. It is about the structure of measurement itself, about what it means to locate a point in space when the act of locating it disturbs the geometry of space irreversibly. This is the place where the energy resolution rule, which has held from visible light through X-rays, through electron beams, through TV-scale colliders, reaches a boundary it cannot cross. Not because the rule is wrong, but because the rule was derived under assumptions that space-time is flat, that the probe does not significantly disturb the geometry. It is probing that ceased to hold at this scale. The rule worked for 20 orders of magnitude. At the 21st, the ground on which the rule stands is no longer there. The question that this raises is not rhetorical. If observation itself becomes impossible below the Planck scale, And if the two greatest frameworks in physics, general relativity and quantum mechanics, both fail to describe what happens there, then what, if anything, does happen there? Whether that question has a physical answer, and what kind of theory would be needed to provide one, is something the energy resolution argument alone cannot tell us. But there is a second, entirely independent line of reasoning that arrives at the same boundary, and it comes not from black holes or gravitational collapse, but from the quantum mechanics of measurement itself. The Planck length is not a measurement anyone has ever made. No experiment has probed it. No instrument has approached it. It sits 20 orders of magnitude below the smallest scale any accelerator has reached, and the argument from the previous section suggests that no accelerator could ever reach it, because the attempt would produce a black hole rather than a measurement. In that sense, the Planck length is a theoretical object, a scale derived not from observation, but from the internal logic of the constants nature has given us. Those constants are three. The speed of light, which governs the relationship between energy and wavelength, and which appears in both quantum mechanics and relativity. The gravitational constant, which sets the strength of gravity, how strongly a given mass or energy curves the spacetime around it. And Planck's constant, which sets the granularity of quantum mechanics, the minimum amount of action that any physical process can involve. Each of these constants has units, and when you combine them in the only way that produces a unit of length, the result is approximately 1.6 times 10 to the minus 35 meters. There is no free parameter here, no adjustable number, no assumption that could be tweaked to produce a different answer. The Planck length is what falls out when you ask, at what scale do gravity and quantum mechanics become simultaneously important? What makes this number meaningful is not that it is small, though it is extraordinarily small, but that it marks the scale where the two most successful theories in the history of physics are both expected to fail. General relativity describes gravity as the curvature of a smooth, continuous spacetime. Quantum mechanics describes matter and energy as inherently probabilistic, granular, defined by uncertainty relations that prevent any quantity from being simultaneously sharp in ways that would violate them. At the scales we have access to, these two theories operate in separate domains. Relativity governs the large, quantum mechanics governs the small, and they rarely need to speak to each other. At the Planck scale, both become relevant simultaneously, and they speak a different language. To get a concrete sense of where the Planck length sits in the hierarchy of scales, start with something familiar. A human hair is roughly 80 micrometers wide, 80 millionths of a meter. A red blood cell is about 8 micrometers, 10 times smaller. A typical bacterium is around 1 micrometer. A virus, perhaps 100 nanometers, 100 billionths of a meter. An atom, about 1/10 of a nanometer. A proton, about a femtometer, 1 quadrillionth of a meter, 100,000 times smaller than the atom. The Planck length is 20 orders of magnitude smaller than the proton. If you started at the scale of the proton and divided by 10, 20 times in succession, you would arrive at the Planck length. The proton already strains imagination. What lies 20 powers of 10 below it is, in any experiential sense, unreachable. At that scale, the smooth geometry that general relativity describes is not expected to hold. The intuition, shared by most physicists who have worked on quantum gravity, is that spacetime at the Planck scale is not a quiet, flat stage on which particles move, but something far more turbulent, a regime where quantum fluctuations in the geometry itself become as large as the geometry. The physicist, John Archibald Wheeler, working on these questions in the middle of the 20th century, coined the phrase quantum foam to describe what he expected this regime to look like. Not smooth, not continuous, something more like the surface of the ocean seen from far above, flat and featureless at large scales, but increasingly violent and irregular the closer you get, until at the smallest scales, you are looking at something that bears no resemblance to the calm surface you saw from a distance. The foam is a conjecture, not a confirmed fact. No experiment has detected it, but the reasoning behind it is straightforward. Quantum mechanics requires that any field, including the gravitational field, which is the curvature of spacetime, must obey uncertainty relations. You cannot simultaneously fix both the value of the field and the rate at which it is changing. At large scales, these fluctuations are tiny compared to the field itself, and they average out to something smooth. At Planck scales, the fluctuations become as large as the field. The geometry stops having a well-defined value. The question of what shape spacetime has at a given point becomes unanswerable, not because the measurement is difficult, but because the question itself may not have a definite answer. The Planck time accompanies the Planck length as a natural partner. It is the time it takes light to cross a distance equal to the Planck length, approximately 5 × 10⁻⁴ seconds. 1 second contains more Planck times than the observable universe contains Planck lengths across its diameter. Below this timescale, the concept of sequence of one event happening before or after another is expected to lose its meaning in the same way that position loses meaning at the Planck length. Causality, the chain of cause and effect that underlies every physical law we know, depends on time having a definite order. At the Planck scale, that order is no longer guaranteed. These scales are not merely the limit of what we can measure. They are, according to the reasoning we have followed, the limit of what measurement means. Below the Planck length, the word distance does not obviously refer to anything. Below the Planck time, the word before does not obviously refer to anything. The concepts that physics uses to describe the world position, duration, sequence, geometry are all built on the assumption that spacetime is a smooth, well-defined background. At the Planck scale, that assumption runs out. There is an irony worth noting here, one that I find harder to move past the more I think about it. The gravitational constant, the constant that appears in the Planck length formula, alongside the speed of light and Planck's constant, is the least precisely measured of all the fundamental constants. The speed of light is known to better than 1 part in a billion. Planck's constant is known to similar precision. The gravitational constant is known only to about 1 part in 10,000, and different experimental measurements of it disagree with each other at levels that suggest we may be missing something about how to measure it. The most fundamental length scale in physics, the one that marks the boundary of all measurement, depends on the one constant whose value we know the least precisely. The Planck length also connects to something that extends beyond measurement into the nature of information. If there is a minimum length, then there is a minimum area, the square of the Planck length, roughly 2.6 × 10⁻⁷ square meters. And if area comes in discrete units at the smallest scale, then the amount of information that can be encoded in any region of space is finite. Not limited by technology or by the density of matter, but finite in principle, bounded by the number of Planck areas that fit on the surface enclosing the region. This is the content of what is called the holographic bound. The maximum information content of any region scales with its surface area in Planck units, not with its volume. A sphere twice as wide does not contain 4 times as much information. It contains 4 times the surface area, and therefore 4 times the information capacity. Volume, at the deepest level, may not be the right measure of how much a region of space can hold. When the thermal radiation that black holes emit was calculated in the 1970s, the result connected to these same Planck scale quantities. The temperature of that radiation depends on the black hole's surface area measured in Planck units. The entropy, the information content of the black hole, is proportional to the number of Planck areas on its horizon. These results, derived from combining quantum mechanics and general relativity in a regime where neither is expected to be fully reliable, were among the first hints that the Planck scale is not merely a limit on measurement, but a fundamental granularity in the structure of physical reality. Whether the Planck length represents a true discreteness, a smallest possible distance in the way that a photon is the smallest possible unit of light, or whether it marks a smoother transition into a regime where our current concepts simply stop applying, remains genuinely open. The two leading approaches to quantum gravity answer this question differently, and neither has yet been confirmed by experiment. What they share is the recognition that something changes at this scale, that the space-time we navigate at every other level of description cannot be the whole story. Werner Heisenberg arrived at his uncertainty principle in 1927, not through experiment, but through a thought experiment about what it actually means to observe a particle. He imagined trying to measure the position of an electron by shining light on it. To locate the electron precisely, you need light with a short wavelength short enough that the electron leaves a distinct mark in the pattern of scattered light. But a photon with a short wavelength carries high momentum, and when it scatters off the electron, it transfers some of that momentum to it. The more precisely you locate the electron, the harder you kick it, and the less you know about where it is going. The more gently you probe using a long wavelength, low momentum photon, the less disturbance you cause, but the less precisely you can determine the position. What Heisenberg showed was that this is not a limitation of any particular experimental technique. It is a constraint built into the structure of quantum mechanics itself. The product of the uncertainty in position and the uncertainty in momentum can never fall below a fixed value determined by Planck's constant. No improvement in detector technology, no refinement of technique, no increase in experimental care can reduce that product below the limit. The fuzziness is not noise in the measurement. It is a feature of the particle itself, or more precisely, a feature of what it means to have definite values for position and momentum simultaneously, which quantum mechanics says is simply not possible. This principle held up through every experimental test that followed. It proved essential to understanding atomic structure, chemical bonding, the behavior of electrons in materials, the stability of matter itself. A hydrogen atom does not collapse, the electron does not spiral into the nucleus, because the uncertainty principle prevents the electron from being simultaneously near the nucleus and nearly stationary. Confine the electron more tightly, and its momentum uncertainty grows, pushing it outward. The atom finds a stable size where these competing pressures balance. Remove the uncertainty principle and every atom in your body would collapse in a fraction of a second. But Heisenberg's original derivation, and the principle it produced, made an assumption that was invisible at the time because it seemed so obviously true. It treated space-time as a fixed, inert background, a stage that the particles perform on, but that is not itself affected by what happens on it. The photon scatters off the electron, kicks it, disturbs its momentum. But the space in which this happens stays flat, stays well-defined, stays unaffected. This is the assumption that general relativity quietly undermines. General relativity says that energy curves space-time. Any energy, including the energy of the photon you are using to locate the electron, at the energies involved in a typical measurement, the curvature produced by the photon is absurdly small, far too small to affect anything. A single visible light photon curves spacetime by an amount that no instrument could ever detect. The assumption that spacetime stays flat is, for all practical purposes, correct. But follow the logic to higher energies. To resolve a smaller position, you need a shorter wavelength photon, which carries higher energy. Higher energy means more spacetime curvature around the region being measured. At first, the curvature is still negligible. But as the required position precision approaches the Planck length, the energy of the measuring photon approaches Planck energy, and the curvature it produces becomes comparable to the size of the region being probed. The photon is no longer a gentle probe moving through flat space. It is a significant source of gravity in its own right, deforming the very coordinates it was meant to measure. The gravitational disturbance the photon introduces adds a new source of position uncertainty, one that grows with energy rather than shrinking. In the ordinary Heisenberg relation, increasing the photon's momentum reduces position uncertainty. Once you include the gravitational effect, increasing momentum also increases the gravitational disturbance, which increases position uncertainty through a different channel. These two effects, quantum uncertainty decreasing with energy, gravitational uncertainty increasing with energy, pull in opposite directions. They reach a balance at a specific energy, and at that energy, the total position uncertainty reaches a minimum. That minimum is the Planck length. Below that scale, adding more energy to sharpen the measurement does not reduce uncertainty, it increases it, because the gravitational term begins to dominate. The modified relation that captures this behavior is called the generalized uncertainty principle, and it arises independently from the black hole argument reached earlier, through entirely different mathematics, starting from different premises and arriving at the same number. Two roots into the same wall. The detail that stopped me when I first worked through this carefully is that neither argument requires the other. The black hole argument comes from general relativity. Concentrate enough energy in a small enough region, and a horizon forms. The generalized uncertainty argument comes from quantum mechanics. Add a gravitational correction to Heisenberg's original thought experiment, and a minimum position uncertainty appears. You could know nothing about black holes and still derive the Planck length from the uncertainty argument. You could know nothing about uncertainty principles and still derive it from the black hole argument. The fact that both roads lead to the same destination, expressed in the same number built from the same three constants, is not a coincidence that physics has produced accidentally. It is a signal that something real sits at that scale, something that both theories are separately sensing but neither can fully describe. The generalized uncertainty principle also changes how information enters the picture. If there is a minimum measurable length, then the amount of information that can be specified about any region of space is finite, bounded by the number of Planck scale cells that fit in that region. Not just practically finite, as in limited by available technology. Finite in principle, as a consequence of what measurement means at the smallest scale. A region of space does not contain an infinite number of distinguishable states. It contains a number determined by its geometry measured in Planck units. This has an implication that extends to black holes. When a black hole forms, everything that fell in every particle, every configuration of matter, every bit of information about what was there is hidden behind the horizon. Whether that information is permanently lost or merely inaccessible became one of the central unsettled questions in theoretical physics over the last half-century. The connection between the Planck scale and information capacity, the idea that information is stored in Planck area units on surfaces rather than in volumes, is one of the few threads that suggests the question might have an answer. Not that we have the answer, but that the Planck scale, which first appeared as a limit on measurement, keeps reappearing in the accounting of information whenever gravity and quantum mechanics are made to confront each other. Heisenberg's original principle was a statement about electrons and photons in flat space. The generalized version is a statement about the structure of spacetime itself, about what the universe will and will not allow to be specified. The same logic that prevents you from knowing an electron's position and momentum simultaneously, extended to include the geometry of the space the electron moves through, produces a minimum length below which position has no meaning at all. Not uncertain, undefined. Whether the generalized uncertainty principle is the correct modification of Heisenberg's relation, whether it captures the actual behavior of quantum gravity, or whether the true theory will produce something subtly different is not yet known. It is a strong argument built on solid physical reasoning, confirmed by the fact that it appears independently in string theory and in loop quantum gravity as well. But it remains a theoretical result, waiting for a context in which it could be tested. What it points toward is clear: a regime where uncertainty is not just a feature of particles, but a feature of the space they occupy, where the background that physics has always taken for granted turns out to be as uncertain as everything that moves through it. The problem that string theory was built to solve is older than string theory itself, and it sits at the intersection of the two frameworks that dominate modern physics. Quantum field theory, the framework that describes particles and forces at small scales, works by treating elementary particles as points. Zero-dimensional objects with no spatial extent, no size, no internal structure. Just a location, a charge, a mass. This simplification is enormously productive. It underlies the most precisely tested theory in the history of science, and its predictions have been confirmed to more decimal places than almost any other result in physics. The point-particle assumption works until you try to include gravity. When you attempt to write down a quantum theory of gravity using the same point-particle framework treating the graviton, the hypothetical carrier of the gravitational force, as a point particle like the photon or the electron, the calculation produces infinities. Not large numbers that can be managed or approximated away. Actual infinities appearing at every order of the calculation that make the theory's predictions meaningless. The same renormalization techniques that salvage infinities in quantum electrodynamics fail for gravity. The mathematical structure of the gravitational interaction at the quantum level is incompatible with the point-particle assumption in a way that cannot be repaired within that framework. The source of the problem is geometric. When two point particles interact, all of the interaction energy is concentrated at a single point, a region of zero volume. Energy density is energy divided by volume. At zero volume, the energy density of the interaction is infinite. In electromagnetism, the infinities this produces can be absorbed through a procedure that effectively redefines the particle's charge and mass, a procedure that is mathematically consistent, even if conceptually uncomfortable. In gravity, where the interaction itself is geometry, and where infinite energy density means infinite spacetime curvature, the infinities cannot be absorbed. The geometry of the calculation collapses into a singularity at the interaction point. String theory dissolves this problem by replacing the point with a line. Not a line extending through ordinary space, but a one-dimensional object, a string whose length is of the order of the Planck length, roughly 10 to the minus 35 meters. When two strings interact, they do not meet at a point. They approach each other, overlap, exchange energy along a finite length, and separate. The interaction is spread over a small but non-zero region. The energy density remains finite throughout. The singularity at the interaction point disappears. Because there is no interaction point, only an interaction region with a definite size. The infinities that wrecked quantum gravity in the point-particle framework do not appear. This alone would make string theory interesting. But the deeper consequence appeared when theorists began cataloging the possible vibrational modes of these strings, the different ways a string can oscillate, analogous to the different harmonics of a stretched wire. Each distinct pattern of vibration corresponds to a distinct particle with distinct properties. A string vibrating in one mode might behave like an electron. Another mode might behave like a photon. Working through the mathematics of all possible modes, theorists found one mode that was unavoidable, a massless particle with spin 2, which is precisely the set of properties that any quantum theory of gravity requires the graviton to have. gravity had not been put into string theory. It had fallen out of it. The attempt to build a consistent quantum theory using one-dimensional objects instead of points had produced, without any additional assumptions, exactly the particle that a quantum theory of gravity requires. For physicists working in the 1980s, when this connection became clear, it was striking enough that string theory shifted from being a candidate model for the strong force, its original context in the late 1960s, to a candidate for a unified description of all forces and all matter. The unification requires extra dimensions. A string vibrating in 3 spatial dimensions has a limited number of possible modes. To produce the full range of particles and forces observed in nature, strings need more room mathematically, either 9 or 10 spatial dimensions, depending on the version of the theory. The additional dimensions are not observable because they are compactified, curled up at scales close to the string length itself, too small to affect any measurement at accessible energies. Their geometry determines which vibrational modes are possible, and therefore which particles exist. Different geometries for the extra dimensions produce different low-energy physics, different particle masses, different force strengths, different effective laws of nature. The number of geometrically consistent compactifications is vast. Estimates run to 10 raised to the power of 500, a number so large that listing it in full would require more space than the observable universe contains matter. Each compactification corresponds to a self-consistent version of physics with its own particle content and constants. Whether the specific compactification that produces our universe's physics can be identified from the theory, or whether the theory provides any principled way to select among the options, remains one of the most difficult open problems in theoretical physics. The landscape of possibilities is real, but navigating it has proved harder than the early optimism of the 1980s suggested. What string theory does provide, regardless of these unresolved questions, is a specific mechanism for why probing shorter distances stops working at the string scale. At low energies, strings behave as point particles, and the energy resolution rule holds. Higher energy reveals shorter distances. As energies approach the string scale, the strings begin to stretch. Adding more energy no longer shortens the effective probe wavelength. It excites higher vibrational modes and increases the string's spatial extent. The string grows rather than shrinks. Resolution stops improving. Below the string length, the concept of distance encoded in the theory's geometry begins to change character. What looks like a very small compactified dimension becomes, through a duality in the mathematics, equivalent to a large one. Short distances and long distances are related by symmetry. The geometry doubles back on itself. This is called T-duality, and it is one of the more surprising structural features of string theory. A string moving in a dimension compactified to radius r has the same physics as a string moving in a dimension compactified to a radius proportional to the inverse of r. Making the dimension smaller beyond a certain point is physically equivalent to making it larger. There is a minimum radius of the order of the string length below which the notion of making something smaller has no operational meaning within the theory. The minimum length is not imposed by hand. It emerges from the symmetry structure of the theory itself. String theory has not been experimentally confirmed. The energies required to directly observe string behavior are Planck scale energies, which no conceivable accelerator could reach. Indirect signatures, particular patterns in gravitational waves, specific predictions for particle masses, or interactions at energies above current accelerator reach have been proposed, but none have yet provided a clear test. The theory's mathematical consistency is remarkable, and the fact that it reproduces general relativity and the known particle physics at low energies is a significant constraint. But a theory that is mathematically consistent and reproduces known results is not, by itself, confirmed. It is a candidate. The honest position on string theory is this: It solves the problem it was designed to solve. It produces gravity without putting it in by hand. It builds in a minimum length through its own symmetry structure, and it remains, after decades of intensive work, the most developed framework for combining quantum mechanics and gravity that exists. Whether it is correct about the actual structure of nature at the Planck scale is a question that current physics cannot answer. There is a second framework for quantum gravity that begins from entirely different assumptions, not from the behavior of matter, but from the geometry of space itself, and it arrives at the minimum length through a different route entirely. String theory arrived at the Planck scale from the direction of matter by asking what happens when you replace point particles with extended objects. Loop quantum gravity arrives at the same scale from the opposite direction, by asking what happens when you apply quantum mechanics not to the particles moving through spacetime, but to spacetime itself. The starting point is not matter. It is geometry. General relativity describes gravity as the curvature of spacetime. Mass and energy curve the geometry around them, and other objects follow the curves. This is not a metaphor for some other process, it is the process. Gravity is geometry. Einstein's equations are equations about how geometry evolves in response to the distribution of energy and matter. They are, in that sense, equations about space and time themselves rather than about objects moving through space and time. Quantum mechanics, applied to any physical system, produces a theory where the system's properties take on discrete values at small scales and are described by probability distributions rather than definite states. Applied to the electromagnetic field, it produces quantum electrodynamics, where light comes in discrete packets. Applied to the nuclear fields, it produces the quantum chromodynamics of quarks and gluons. Loop quantum gravity asks what happens when the same quantization procedure is applied to the gravitational field to space-time geometry itself. The answer the mathematics returns is that geometry becomes discrete. Area and volume, like energy and charge in other quantum theories, can only take on specific allowed values. Between those values, there is nothing, not smaller geometry, not approximate geometry, but no geometry at all. The allowed values form a spectrum, and the smallest non-zero value of area in this spectrum is of the order of the Planck length squared, approximately 10 to the minus 70 square meters. To give that some grounding, a proton's cross-sectional area is roughly 10 to the minus 30 square meters. The minimum quantum of area in loop quantum gravity is 40 orders of magnitude smaller than that. A proton, already beyond the threshold of direct visualization, contains within its cross-section roughly 10 to the 40th minimum area quanta. The granularity of space, if loop quantum gravity is correct, is as far below the proton as the proton is below a region of space large enough to contain 10 billion observable universes stacked side by side. The mathematical structure that encodes this discrete geometry is called a spin network. A spin network is a graph, a collection of nodes connected by links where each link carries a label that determines the area of the surface it passes through, and each node carries a label that determines the volume of the region it represents. The geometry of space, in this framework, is not a smooth background that exists independently of what is in it. It is the network itself. Space is not a container. It is a pattern of relationships between adjacent quanta of volume encoded in the structure of the graph. At scales far larger than the Planck length, at every scale accessible to any measurement ever made, this discrete structure averages out to something indistinguishable from the smooth geometry of general relativity. The same way a material that is granular at the atomic scale appears continuous and smooth to any instrument operating at larger scales, the spin network appears as a smooth, curved spacetime when viewed at the scales of atoms, planets, and galaxies. General relativity is not contradicted by loop quantum gravity. It is recovered from it as an approximation that becomes exact in the limit of large scales. The smooth spacetime of Einstein is what the spin network looks like from far away. Time in this framework is also discrete, progressing through a sequence of spin network configurations rather than flowing continuously. Each transition from one configuration to the next is a quantum event, a single tick of the universe's most fundamental clock. The duration of each tick is of the order of the Planck time, roughly 5 × 10⁻⁴ hupseconds. In 1 second of ordinary time, approximately 10⁴ such ticks occur. Continuity of time, like continuity of space, is a large-scale appearance that dissolves at the Planck scale into a sequence of discrete transitions. One of the structural consequences of this discreteness is that the singularities predicted by classical general relativity cannot form. A singularity in general relativity is a point where curvature becomes infinite and the equations break down the center of a black hole, or the initial state of the Big Bang. In loop quantum gravity, infinite curvature requires infinite energy density in an infinitesimally small volume. Since volume comes in discrete non-zero quanta, the denominator never reaches zero. The energy density reaches a large but finite maximum. The Planck density and the equations remain well defined. The singularity is replaced by a region of extreme but finite curvature. Applied to cosmology, this has a direct implication for what happened at the beginning. In classical general relativity, tracing the universe backward in time leads to a singularity, a point of infinite density and zero volume at a finite time in the past. In loop quantum cosmology, the branch of the theory applied to the universe as a whole, tracing the universe backward leads not to a singularity, but to a bounce. The universe contracted to a minimum volume set by the Planck scale and then re-expanded. The Big Bang, in this picture, was not a beginning from nothing. It was a transition from a prior contracting phase. Whether the physics of that prior phase could have left observable imprints in the current universe, in the detailed pattern of temperature fluctuations in the oldest light we can detect, for instance, is an active area of research. The signals predicted are faint, and current instruments have not yet been able to confirm or rule out the hypothesis. The experimental situation for loop quantum gravity resembles that for string theory in one important respect. Direct tests at Planck scale energies are not possible with any foreseeable technology. But there are indirect searches. If spacetime has a granular structure at the Planck scale, photons of different energies traveling across cosmological distances might accumulate tiny differences in travel time because the granular geometry would interact slightly differently with photons of different wavelengths. Over billions of light years, even an incredibly small per-photon effect could accumulate into a measurable delay. Gamma-ray bursts, brief, intense flashes of high-energy light from distant catastrophic events, provide a natural test. A burst produces photons across a wide range of energies simultaneously. If the highest energy photons systematically arrive slightly earlier or later than the lowest energy ones, after accounting for all known effects, it would be a signal of Planck scale spacetime structure. Data from multiple gamma-ray bursts observed over the past 2 decades has constrained this effect to very small levels, currently ruling out the simplest linear versions of the predicted dispersion. Whether more subtle versions survive is still being tested. What loop quantum gravity and string theory share, despite approaching the problem from opposite directions, one from matter, one from geometry, is the conclusion that the Planck scale is not merely a limit on measurement, but a fundamental feature of physical reality. In string theory, a minimum length emerges from the symmetry structure of the theory. In loop quantum gravity, it emerges from the quantization of geometry. 2 independent mathematical frameworks, built on different assumptions, using different tools, both finding that space cannot be subdivided without limit. That convergence does not prove either theory is correct, but it is a signal worth attending to that whatever the correct theory of quantum gravity turns out to be, a minimum length near the Planck scale is likely to be one of its features. There is a detail in the loop quantum gravity program that I find harder to move past than most. The theory quantizes geometry without needing to add new particles, new dimensions, or new fields. It takes the one thing Einstein gave us, the identification of gravity with the structure of spacetime, and asks what quantum mechanics does to that structure directly. The answer it produces is that space, the thing we have always treated as the background in which physics happens, turns out to be as quantum as everything that moves through it. The background is not background. It is a physical system with its own quantum states, its own fluctuations, its own minimum scale below which it simply does not have a well-defined geometry. Everything we have measured and calculated and built our understanding of the universe on, all of it, has been conducted inside a system whose deepest properties we have not yet accessed. Everything built in this journey rested on one assumption so fundamental that it was never stated: that space is a smooth, continuous background in which distances have definite values. Every ruler, every detector, every particle beam, every calculation in the history of physics has made that assumption. It is the ground under every measurement ever taken. What the Planck scale tells us is that the ground runs out, not because our instruments are insufficient, because the concept of distance itself, extended below a certain scale, stops referring to anything physical. The two arguments that establish this, one from black hole formation, one from the modified uncertainty principle, arrived at the same number through entirely different mathematics. That convergence is not an accident of calculation. It is the two most successful frameworks in physics independently sensing the same boundary and expressing it in the same units. The boundary does not mean that space ends. It means that space, as we have always understood it as a smooth, infinitely divisible, passively neutral background, is an approximation. A very good approximation, accurate across every scale from the largest structure in the observable universe down to distances 100 billion times smaller than a proton. But an approximation nonetheless. Something deeper underlies it. Something that the approximation of smooth spacetime obscures at every scale we can access, and only begins to reveal itself at scales we cannot reach. The question this raises is, if spacetime emerges naturally, if it arises from something more fundamental, the way temperature emerges from the motion of molecules, or solidity emerges from the arrangement of atoms, then what is that deeper, more fundamental thing? Two frameworks have offered partial answers, each approaching from a different direction, each capturing something real while leaving something else unresolved. String theory built its answer from matter. Replace point particles with extended objects, and the infinities that destroy quantum gravity dissolve. Gravity emerges from the vibrational modes of strings without being put in by hand. A minimum length appears from the symmetry structure of the theory. The framework is mathematically rich, internally consistent, and produces general relativity at low energies. It has not been confirmed by experiment, and the landscape of possible solutions it generates, the vast number of distinct compactifications of extra dimensions, each producing different physics, has made it difficult to identify which solution, if any, corresponds to our universe. Loop quantum gravity built its answer from geometry. Apply quantum mechanics directly to spacetime, and geometry becomes discrete. Area and volume come in minimum non-zero quanta. Singularities cannot form because volume cannot reach zero. The Big Bang becomes a bounce from a prior phase rather than a beginning from nothing. General relativity is recovered at large scales as the smooth limit of a fundamentally granular structure. It has also not been confirmed by experiment, though searches for signatures of space-time granularity and high-energy photons from distant gamma-ray bursts continue to constrain its predictions. Both frameworks agree on the thing that matters most for this question. Space and time are not fundamental. They are features that emerge at large scales from something whose character we do not yet fully understand. The smooth geometry that underlies every measurement ever made, every distance, every duration, every location is a large-scale average over a deeper structure that looks nothing like a smooth geometry at the scales where that structure actually lives. There is an idea developed over the past few decades at the intersection of quantum gravity and quantum information that goes one step further. It suggests that what the deeper structure is made of is not geometry at all, but entanglement. Two quantum systems that are entangled share information in a way that has no classical analog. Their states are correlated regardless of the distance between them in the spacetime we observe. The proposal is that spacetime distance is itself a consequence of the degree of entanglement between quantum systems. Regions of space that are close together correspond to systems that are strongly entangled. Regions that are far apart correspond to systems with weak entanglement. The geometry of space encodes the entanglement structure of an underlying quantum system, not the other way around. If this is correct, then distance is not a property that space has independently of the matter and energy within it. It is a relationship between quantum systems, expressed as a geometric quantity at large scales. Space is not the arena in which physics happens. It is a way of describing how quantum systems relate to each other, a language that works at the scales we inhabit, but that breaks down when you try to push it below the Planck length, because below that scale, the entanglement structure no longer translates cleanly into geometric language. The holographic principle connects to this at a specific technical point. It holds that the information content of any region of space is bounded not by the region's volume, but by its surface area measured in Planck units. A region of space 10 centimeters across does not contain more information than a region 1 centimeter across by a factor of 1,000 the volume ratio. It contains more information by a factor of 100 the surface area ratio. The implication is that the degrees of freedom that constitute physical reality are not distributed through the volume of space. They live on surfaces. The three-dimensional interior is in some sense a projection of a two-dimensional boundary. This was not proposed as a philosophical position. It emerged from the mathematics of black hole thermodynamics from the calculation of black hole entropy, which turned out to scale with horizon area rather than the volume enclosed, with each Planck area contributing exactly 1 bit. None of this has been experimentally confirmed at the level of direct observation. The ideas are coherent, mathematically grounded, and mutually consistent across several different lines of argument. But they remain theoretical maps drawn at the edge of what physics can currently test. Gravitational wave observatories operating now, and those planned for coming decades, may provide indirect constraints. Precise measurements of how gravitational waves propagate across cosmological distances could reveal whether spacetime has properties at small scales inconsistent with classical general relativity. The signals would be faint. The measurements would require extraordinary precision over extraordinary distances. The possibility exists. What already stands, without needing further confirmation, is the logical structure of the argument we have followed. A rule: higher energy, finer resolution held from visible light through electron microscopes, through nuclear scattering, through the highest energy collider ever built. That rule, followed honestly to its limit, produced not a finer and finer image of nature's foundation, but a boundary where the act of probing becomes the act of obscuring. Two independent roots of reasoning from different branches of physics located that boundary at the same scale and expressed it in the same number. The number emerged from three constants: the speed of light, the gravitational constant, Planck's constant, combined in the only way that produces a length. No free parameters. No adjustable assumptions. Just the constants themselves, pointing at a scale and saying, "Here is where the language you have been using runs out." Physics has been in this position before. Classical mechanics ran out at atomic scales, and quantum mechanics replaced it not by contradiction, but by containing it as a limiting case. Classical spacetime will be contained in whatever comes next in the same way. The smooth geometry of general relativity will remain exactly right at every scale where it has ever been tested. The new theory will reduce to it there and go further, into the regime where general relativity's assumptions dissolve. We do not yet have that theory. The frameworks we have: string theory, loop quantum gravity. The entanglement proposals are candidates. Serious ones, with real mathematical content and real physical insight. But not yet a finished theory confirmed against the world. That is where things stand. Not at a dead end, at a genuine open problem. One of the most precisely located open problems in the history of science. We know approximately where the boundary is. We know what properties the theory that crosses it must have. We know the two frameworks that have so far come closest, and we know what each of them gets right and what each of them leaves unresolved. The problem is hard, and the tools needed to solve it may not yet exist. But the boundary has a name, a location, and a clear statement of what it means. That is not nothing. It is the result of a century of physics following a single rule, honestly and relentlessly, until the rule reached its own limit and pointed past itself. If you have stayed with this all the way here, through the wavelengths and the electron beams, through the quarks and the Higgs field, through the black holes and the uncertainty principle and the spin networks, I want to say something simply. This is hard material. The people who have spent their lives working on these questions have not found it easy. The fact that you have followed it, quietly, in the dark, at the edge of sleep, is its own kind of attention. The universe does not often get that quality of attention paid to it. Rest now. Whatever questions are still open, and there are many, they will be here when you return. The boundary is patient. It has been waiting at 1.6 times 10 to the minus 35 meters for the entire history of physics, and it will wait a little longer.